All right, calculus, we are going to find the volume using disks. Now, this is not necessarily a super challenging section, but it's a little bit hard for me to get the visual pieces across, so I'm going to do my best, and we're going to use some YouTube videos too, but hopefully it'll be fine. It says, look at the graph of y is equal to negative x plus 5. Okay, that graph is not here. We're going to draw. Oops, why is it not doing it? Okay. Ugh, whatever. So negative x plus 5, we know it has a y-intercept of 5. 1, 2, 3, 4, 5. And a slope of negative 1, which means 2, 3, 4, 5. It is going to go from here to there. Okay, I'm going to make that a little nicer. And of course, we know that this line goes on forever and ever in both directions, but for right now, we are going to focus on this. Just this piece of this line, right? This is the line y is equal to negative x plus 5. All right, then it says, if the area bounded by the graph, okay, so this, the y-axis, this, the x-axis, that. So basically, if this triangle were revolved around the x-axis, so I'm taking this triangle and I'm going around that way, what type of figure would be formed? Try and picture this in your mind as I help you along, but hopefully, if you're playing along at home, as we rotate this, we are going to get here, this is going to be a big circle, and maybe here is going to be a less big circle, and I'm going to draw it like that. And then here's just going to be like a tiny circle, right? But we are going to get a cone. Hopefully you can kind of see the three-dimensionalness of this cone, but we've got, oh, I'm going to undo that. Oh, it's so hard to write with this thing. Okay, we're fine. It's got this outer layer, and then it's got this inner piece, like I would be able to go into this cone, basically. That's not really important. If that was not a very good visual, let me just quick go here, and I'm going to show you another. It's not the same graph, but it gets the idea across. So we've got the square root of x rotated around the x-axis, and that was just to see the shape. If I took it and made a three-dimensional thing, I'd have this kind of curved cone figure. Okay, back to our problem. This is not the question at hand, not what is the shape. Well, I guess it was the question at hand, but it's not really the one we are super interested in. The question is really, what is the volume of this thing? What is the volume of the figure that is formed? Now, that seems like a fairly challenging question to answer, but it's really not. If we use some calculus, we're going to be able to answer this question fairly quickly. To find the volume of this cone, we are going to add up. We are going to add up technically every circle that makes up the cone. That makes up our cone. Now, this is another thing that I would have done in class, but not really here. If you imagine a deck of cards, all right, and I have the deck of cards in front of me, each individual card is like the area that I'm talking about, but then the entire deck would be a volume. So if I take the area of this specific circle, and then I add the area of this circle right here, and I do every circle in here, technically, I am finding the volume. Okay, so how do we do that? Well, notice I made two small things. So we are going to add up. So we're finding a sum, which integrals are sums. And I put every in quotes because technically we're finding the limit as I get all these little circles in here, but I can't really find every single one, at least not by hand. So let's think about this. I am adding up, finding an integral of every one of these circles. So technically we need the area of one of these circles. I'm doing it from left to right. Specifically, I know it's around the x-axis because that's kind of like if I imagine I've got this circle when I'm going from left to right on this x-axis. So this is all with respect to x. And if it's with respect to x, that means the first circle is at x equals 0, and the last circle is at x equals 5. How do we know 5? Again, because of the line here, it has a slope of -1, down 1, over 1, down 1, over 1, etc. Okay, so we're getting closer. Now the question is, what's the area of any of these circles? And it's going to be different, right? I can ask you the area of this first circle right here, but that doesn't really help us because we want the area of every circle in this piece right here. I guess the first question we need to answer, though, is what's the area of a circle, just in general? Area of a circle, hopefully you remember it, is pi r squared. Okay, so really the only thing we need to figure out is what would our radius be here? But again, we need to make sure it's general so that this radius is with respect to x. Or I can find this radius right here and it doesn't really matter. It doesn't need to be specific to that actual piece. Well, what distance are we talking about? We're talking about the y distance here, right? R, the radius, is the y value of this line. And because we need to do this with respect to x, I need to figure out what y is with respect to x. But good news, we have that equation right here. Y is equal to -x plus 5. So I can do a little more work here. I can write the integral from 0 to 5 of pi, our radius, which was -x plus 5 squared with respect to x. And that, my friends, is going to find the volume of this beautiful cone. So let's find it together. If I want to calculate this integral, it's probably going to be a good idea to square this term or FOIL it. And I also am going to pull the pi out. So I'm going to write this as pi times the integral from 0 to 5 of, I'm going to FOIL this kind of quickly for you, so hopefully you're doing the same thing here. X squared minus 5x minus 5x plus 20, it's supposed to be 25, all with respect to x. Technically, I still have that pi and the integral from 0 to 5, x squared minus 10x plus 25, all with respect to x. Now I can take the antiderivative. I'm going to still keep this pi out on the left here. I don't really feel like dealing with it. So I have x cubed over 3 minus 5x squared plus 25x. And we are evaluating this from 0 to 5. Good news, that 0 piece isn't really going to matter because every term here has an x in it. So I can kind of skip that and just plug in my 5. So pi times the quantity 5 cubed over 3 minus 5 times 5 squared plus 25. Again, I'm not writing very well here. 25 times 5. If you want to pause, type this all into your calculator. I'm just going to tell you an approximation here. Hopefully, you get 130.89, and technically we don't know the units, so I'm going to say units cubed. Remember, this is a volume. Now, you might be like, so what, Ms. Wizik, I don't believe you. Well, we know this is a cone, so technically we could have used, we could have used the formula for volume of a cone, which probably is not something you remember. It's definitely not something I remember, but volume of a cone, we're just going to double check our work. We're going to check that the calculus we just did checks out with the geometry that is actually a fact. So the volume of a cone is 1/3 pi r squared times the height. In this case, 1/3 pi, the total radius of that cone would have been that 5. So 5 squared, and then the height was also 5, which, spoiler alert, when I multiply it all out, it gets me the 130.89, which should make you happy, because I don't remember this formula, but you're going to have to remember how to do this calculus. let's generalize what we just did. So finding the volume of a solid using the disk method. I'm going to draw us a little picture. Oh, I don't want red. I guess it doesn't really matter. So let's say I have a curve, and the curve looks something like this. If I want to find the volume of this solid, as I mentioned, we are technically finding a bunch of circles here, and we're finding the area of each of those circles and adding up, oops, you get the picture, and adding up those areas so that we have this volume. So to do this, I am technically finding the volume. I'm going to take the antiderivative, find an integral of the area of one circle, the area of a circle, which again we know is pi r squared. And it's going to technically be either with respect to x or y. We'll see an example of that. So the volume, that's v, obviously. And that's what we got. That's really it. Now, the good news here is this r value always needs to be the same. Not good news, I guess, but whatever. Our r value needs to be the same variable as what we are doing this with respect to. Which means if we are doing this with respect to x, so from left to right, then we need our radius to be the y distance, but technically in terms of x, and vice versa. So let me write that down. If you are integrating with respect to x, okay, so dx, then we would technically want our r to be equal to y in terms of x. You'll see this more in the examples we do, so I think that's probably enough for right now. Let's do another problem though. Here's what we got. The region bounded by the curve y is equal to e to the negative x, and the x-axis between x equals 0 and x equals 1 is revolved around the x-axis. Find the volume of the solid. First, I'm just going to kind of draw what we have here. We are going to have some, oops, basically this weird looking shape, right? Where it's almost like a, I don't know how we would describe this shape. Maybe I'm not making it any clearer, but whatever. Here's our shape, three-dimensional. And if I want to find this, I need to make sure I find my radius, my r. Because I am revolving it around the x-axis, so around like that, I am doing it with respect to x. So my integral is going to be from 0 to 1. How do I know? Well, they gave me these bounds. 0 to 1. I'm going to add in that in a moment. It's with respect to x. And now I need to find the area of one of these circles. Pi, I know, that's a given. Our r is our y value, but we have that too. So e to the negative x squared. Honestly, that's it. Now we're done, other than the fact that technically this is a bit of a challenging integral. But we can do it together because we're so smart. So let's do this. I'm going to pull out the pi. We never feel like dealing with pi, right? So I have pi on the outside, integral from 0 to 1. What do we do when we have something squared? Well, we're going to multiply those exponents. So I really have e to the negative 2x, all with respect to x. Now, you could potentially do this problem just by looking at it, but I'm going to do it with u substitution just because we haven't done that for a while. So I'm going to have my u to be negative 2x. That means du is negative 2 dx. That means my integral becomes pi from 0 to 1 e to the u times du all over negative 2. Look at how much easier that is. This negative 2 then I'm going to pull out front, so I really have pi over negative 2, still the integral from 0 to 1 of eu du. This is not bad, right? The integral of e to the x is just e to the x. So I still have negative pi over 2 e to the u, and I'm evaluating it from 0 to 1, but I do want to remember that these are technically still with respect to x. So I want to make sure I quick plug back in my x's. So I have negative pi over 2 e to the negative 2x, and I want to evaluate that from 0 to 1. Wow, that was not bad. When evaluating, I have negative pi over 2. I'm just going to hold that out here, and I'm going to plug in e to the negative 2 times 1, which would be negative 2, minus e to the 0 power. And this is not anything we really know, so I'm going to plug this into my calculator and get 1.358 units cubed. That's my solution. This one I don't have a fun volume formula to check it for you, but maybe you had paused the video earlier and you just went through and watched it and you're like, yeah, I got the answer correct. So try some of the problems on the homework. We're going to do another example tomorrow. Otherwise, ask questions if you need, and I will talk to you soon.